So now on to the second demonstration of the tests and the results that we are collecting for the special senses. We're on to color deficiency tests, and we're going to do the color deficiency test caps. The test caps are the first way to sort of get a feel for if somebody has color deficiency. Typically in red cones or green cones, those are the most common, and it's the most common in males and not females because the genes coding for the color pigments are located on the X chromosome. Okay, so we've got this little case and it has all these color test caps, and there's a standard baseline blue that's adhered in there, and the goal is for Lola to put them in the order of color similarity, going from like blue all the way out to like the pinky mauve type colors. Okay, so she's gonna do this test. It's really easy to do. You kind of just put it in order. Now, someone that is red-green or red or green colorblind will have issues with putting these in order of similarity or similarity in the hues. Oh, is the light?
It's like shadowed. Just,
oh, sorry. Like this?
Yes.
Okay. Sorry, I'm not a great videographer here.
Slacking.
We went on a hike today. We've been quarantined, but we did go on a big hike, so that was good. Las Trampas in San Ramon. Are you eating another cookie? Oh, McKay, no more cookies, please. The experimenter is slacking on the job.
Okay, I'm gonna call that a day.
So are you sure? Are you positive?
Yes.
Okay, looks beautiful to me. We've almost got a rainbow going there.
Okay.
Let the experimenter, but put the Oreo down.
You don't have to lock it.
You can, I just don't want him to fly over. And then he's going to flip it. Okay, so we close the case, we flip it over, and they're numbered. So we can check whether they're in chronological order or not.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
Beautiful, perfect. You have no color deficiency. That's often called color blindness, but that's kind of a misnomer because they're not blind. Just having a deficiency in one of the types of photopigments or cones. So for the data section in the lab manual, I would write this in here. Here is the color vision deficiency test caps. And so Lola did it perfectly. So I would basically connect, she had them in order. So she had from 1 to 2, 2 to 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Perfectly in order. Now, I'm going to give you an example. If she didn't, and she was colorblind, and she went maybe 1 to 2, but then from 2, right next to 2, she put 13, I would connect 2 to 13. And then if she put 13 next to 12, I would connect to 12. And then 11, and then maybe she put 3 right next to 11, and I would connect 11 to 3. Basically tracing how the order the subject put them in. And if they line up parallel, like her connections, if she did it in that way, they would be parallel to the protan, for example. This would mean she has protanopia, or the lack of red color photopigments, cone photopigments. If it was parallel and lined up with the deutan, with this line right here, that would indicate she is lacking the green photopigments or green cones effectively. And if she did it all like this and then lined up maybe with 7 and 15 or 8 went to 14 and it made a parallel line with Triton, I think of Triton like King Triton, blue, this means she would be Tritonopic, or I just spit, I'm sorry, Tritonopic, or lacking the blue cone photopigments, which is the most rare. Most people are red or green colorblind. So this basically, the simple test caps, the way people line them up together, and if it's parallel to these different lines, can indicate what type of cone is potentially missing. Okay, so that's how we recorded the data, and that's how you would interpret this reference cap color test. Going ahead to the color deficiency test known as the Ichikawa charts, we're going to let Emilio administer that one to Lola, and he is going to kind of flip through the pages and ask her, he's going to flip through the page, she's going to flip through the pages and say which which number stands out the most to her. So this is right in the lab manual, goes over Ichikawa charts, and we start on panel 5, and we just have this book available. And basically, we'd put her subject name. So this is Lola. She's 14. Okay, and male, female. She is female. There are gender differences or sex differences when it comes to color blindness. So that's the chart to record the data. All right, starting on page 5, because the first 4 are just demonstration panels to get familiar with the test, the Ichikawa test. You start with actual 5. So you would let us know which number jumps out the most at you, that you can see the most clearly.
Start on page 4. Yeah.
Start on page 5. The first 4 are test plates, and then it starts on page 5.
I see number 2.
No, you're not on the right page.
You said number 2.
So go, the first 4 are test plates. So count 4 through. 1.
2. It says 2 right there, though.
That's where we start the test. So it says plate number 5. It's out of focus. Plate number 5. Okay, so.
Okay, I see 3.
Okay.
I see 2.
Okay.
I see a 4.
Oh yeah, I can see that too. Okay.
A 7.
Okay.
An 8.
Okay.
And then another 4.
Okay.
A 2. A 7. An 8. A 3. 3.
Okay, so stop right there. So the next one, so you did all of them, great. And so what it is I circled the number that jumped out the most, that she saw the most clearly. And if you'll see here, we've got the normal color vision individuals would choose those numbers. So she chose every single one the way someone that has normal color vision would. If she had a red-green defect, she would have chosen the other numbers. And basically what you do is you just add up the number of circled numbers, like the number of circles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Total would be 10. And then here she had no circled numbers, so that's a 0. So that strongly indicates that she's got normal color vision. If someone had circled some of these, you could go on further and characterize, were they protanopic, so lacking the red photopigments or cones, or were they deutanopic, lacking the green? And so you would do those test pages and then circle the number that they would have see the best or the most clear, and then you could figure out, were they normal, protan, deutan, or not. And so in her case, she's normal. I have had many students, especially male students, that are actually have color blindness. So that is actually how the Ichikawa charts work. Just looking at those panels and seeing if the numbers on the different color background, which ones jump out to the subject. Okay, so now we did the Ichikawa chart here, right in the lab manual, and going ahead. There's 2 other tests here in this section we're going to do, and they're called the color after images and the blind spot. This is the one I was excited for and tried to jump ahead to. Okay, so Lola is also going to do those. We'll take the color plate back, and then for this one, you can do this at home too. It's kind of fun. Some of these are kind of fun to do on yourself, and you can do these tests really easy. You can even write and use different colors pages of paper and write on different things. I usually make it thick, so nice thick white. And what we're going to do in this is you look at a piece of color on white paper, and we're going to do red, and she is going to stare at the red color. Try not to look at the white border, but just look directly at the red color for 30 seconds, not making a shadow on it, but just looking straight at it. And then she is going to tell us what color, when we remove the red, what color she sees on the white paper, jump out from the white paper after removing the red. So we'll do about 30 seconds. Ooh, cracking the knuckles. Good job. Okay, so when we remove it, you want to remove it yourself or you want me to yank it? If you yank it away, just stare at that same location and tell me what color pops out at you on the white piece of paper.
Okay. Can I do it?
Yep.
Green.
Oh, okay, very cool. Okay, so she had the red, and okay, so now we're gonna do a different color. Let's do green now. Okay, so same thing with the green. Put a piece of green paper on white background. Stare at only the green color for 30 seconds. And Amelia's gonna try the same thing right there as well, doing the white on red on the white paper. So basically, you guys would be doing all of this in lab. I am instead having my kids do it and then recording the data.
Welcome.
And then, so you can see at least how the tests are performed, the results, and what they mean, how to interpret them, because that's really kind of the important point, is to figure out how to give them and how to interpret the results. Okay, so we've got the green going on here.
Can I?
Yep, you can pull it away.
Red.
Oh, okay, so the red came with the green. All right, so we could also do blue as well, but basically this principle is addressing activation of your cones. So your cones, if you're just looking at that one color, your cones are getting stimulated in the blue range of that color. So all the cones that respond that are in the short and the middle wavelength, so the blue and the green type cones, mostly the blue, are getting highly stimulated and they get kind of overactive, and then you take it away, and so the cones that were not getting activated at all, basically the white paper is kind of all colors combined, and so when you take away that color that was stimulating those sets of cones, they were overstimulated, and now the opposite cones kind of get activated, and so they tell your brain you saw the other color, the opposite or the complementary color. Okay, so it's kind of using the cones, they're getting activated, and you pull it away, but your other cones actually kind of chime in and get activated by the white paper when you remove the blue. So usually it happens with red, you'll see green, with green you'll see red, and when you pull away the blue, sometimes you see kind of an orangish color. All right, and Amelia's gonna pull away the green and then tell us what you see when you pull that green away. Oop, don't pull the paper.
You messed it up.
No, it's your shadow. Your hair
Oh,
was
if your
on it.
shadow was on it, it does complicate
I
it.
did that before
All
and
right,
it
so
worked.
the next test, so we did that one after images, and you would just write it down write your responses in the results section for us. And you can do that at home. You can do it really easy. So my camera is not adjusting well for near and far. It's not doing accommodation like my eyeball would do as well. So the red, she saw green afterwards, and the green, she saw red. Oh my God, it's so sloppy, it's hard to write. And I didn't do yellow, but you can continue the yellow and also the blue and look at those different ones. Okay, so that almost concludes this section of the vision test, different types of vision tests, except for the blind spot. So the last one is the blind spot, and you can use it right in your lab notebook. You can use it here. It says hold the diagram out about 20 inches from your face. So that's pretty far, right? It's about a couple feet out. You hold it like out in front of you like that. Hold it straight up. And what you do is you close your left eye while focusing your right eye on the cross. This has to be kind of right in the middle of your visual field of your right eye with your right eye open. Okay, so you kind of hold it right out so your right eye can fixate kind of in the middle, but you're going to focus on the X. Don't pay attention to the dot or the circle. Okay, and then you're going to slowly bring either this page or the little paper. We just write, you can write it down on a piece of paper and do it like this. We have them all printed up. And then what you do is you bring it closely, slowly to your face with your left eye closed. And then you reach a point where the circle, you found it?
Yep.
Where the dot disappears, okay? So Amelia, you want to hand her the ruler and help with this one? And then put the ruler right up under the eyeball as close as possible without jamming the eyeball and measure out to the paper. And that is the location or the distance where her blind spot is obvious because she cannot see the dot at that point.
11 centimeters.
11 centimeters. Okay, so in collecting this data here, it actually says, okay, measure the distance from your eye to the diagram, record this value. And it was 11 centimeters. Use the following equation to determine the distance between the optic disc and the fovea centralis. Okay, so the optic disc, where the nerve leaves the back of the eyeball, is the blind spot. This is technically considered the blind spot because there's no photoreceptors where all those axons gather and leave in the optic nerve. So you can't see anything. You can't perceive any light or any information at that part of the eyeball. The fovea centralis, on the other hand, is the highest concentration of cones in the back of the eyeball, and it's positioned a little ways away from the optic disc. Fovea centralis has the high concentration of cones. This is your high acuity color vision right there. So this little equation right here, A over B is equal to C over D. All you do is have to plug in those numbers. And the data point that we just collected, the distance from the eye to the paper as measured above, for Lola, it was 11 centimeters. So basically, you would plug in here distance from the X and the dot on the card that we used was 67 millimeters over B, which is the distance between the fovea centralis in the back of the eyeball and the retina and the optic disc in millimeters. And we are going to be solving for B. So B is our X is equal to C, the distance from the eye to the paper. That's what we just measured. Where that dot disappeared as she brought the paper closer to her eye is 11 cent. Sorry, was it 11 centimeters?
Yeah, 11 centimeters.
Okay, centimeters. And then divided by the focal length of the eye. The typical focal length in millimeters is 17 millimeters. So this is an estimate, but it's pretty close to the adult human eyeball focal length. And so if we divide those out, making sure that we have to adjust or do a conversion of centimeters to millimeters, okay? How many millimeters are in a centimeter? 10, okay? So we're gonna have to multiply that by 10.
110.
So that would be 110 millimeters. So that's really what I'm gonna work with for that. We would set up and solve for X. So 67 times 17 is equal to X times 110, right? And then divide by 110. So that will give us our X. And what we're getting for X is B, the distance between your fovea centralis and your optic disc in millimeters. And so we would solve for X to get that number. I don't know if I should plug it out, but basically that's just that simple algebraic equation to solve for that distance between the fovea and the optic disc. Okay, so that concludes the vision part of this. We're going to do a last little segment, a little demo on audition, hearing, and equilibrium. Okay.